very good job for this conference. And I'm sorry that I will not talk about motific Milnor fiber. But in place of talking cyclic L-infinity algebra, I will talk a bit about cyclic L-infinity algebra. But something I want to talk about this numerical invariant. And in a story of Floer homologies, then I think many physics people like to get some numerical invariant, and we mathematicians somehow try to make it well defined, and to get something well defined and numerical in open string or Floer theory is rather difficult. And for a long time, somehow I just keep saying that what is well defined is a vector space, not a number. And but in some special case, we get some numbers. That's something I want to explain today. And the original plan was to talk both in Calabi-Yau case and Fano or toric case. But after I prepared yesterday, I found that to try to both is almost impossible. So today I want to concentrate on a Fano or toric case. And then the main part of this talk is a joint work with Yongin Oh and with Ota and Ono. And this is and what I am going to talk is taken mainly from the paper on the toric paper part 3. And unfortunately, part 3 is not yet on a web, and it is in our machine, most likely, but it's not yet ready to to distribute. But we hope we can do it in a couple of weeks, or at least in a month, but I don't know. So I start discussing with something about the Frobenius algebra. So Frobenius algebra is, you have some H is a vector space, finite dimensional vector space, maybe Z2 graded, over lambda. Lambda is some field. Usually we take a numerical field, but just any field. And this is Z2 graded. And you have two structures. One is just the inner product. And this guy goes to somehow HK, tensor Hn minus K to lambda, and this is perfect. And n is some number, which is supposed to be a dimensions. But this is kind of... You can imagine that this is something like a Poincare duality. And I think... And the other thing is this. This is a associative product. And what we need is just somehow... the most important property is this Calabi-Yau property. I mean, it's kind of cyclically symmetric. I don't know, this is not Calabi-Yau, it's Frobenius property, you're right. Yeah. Calabi-Yau means that this kind of perfect pairing exists, right? It's kind of Calabi-Yau property. And this is Frobenius algebra, and maybe you assume also that this E, so I want to write unitary Frobenius algebra means that you have a unit, maybe 1, in H of degree 0 and just a unit. So, and then I want to define some number. The definition is just so this Z1 of H is just sum over this sign. I want to get rid of sign, and this one I will soon explain. You have some numbers G I2, J2, no, G, J1, 0, G, I2, J2, G, I3, J3 of M, I1, I2, I3, M, J1, J2, J3. So this is a kind of numerical invariant of Frobenius algebra. And I want to explain the notations. And E, large I, and I is from 0 to some large n is a basis of our vector space H. And E0 is a unit. And so then G is just a tensor notation. So Gij is just the inner product of EI and EJ. And this Gij is its inverse. I forgot to say, this has some symmetry, right? Somehow x, y is, I think if I do this degree x, so there are many conventions, but I want to put these conventions. So this is slightly different from symmetric, but it's kind of. And what is this? Yeah. And that Mij is just M, I, J, K is this product structure. I'm sorry, EI. This is a kind of matrix coefficient of this product structure with respect to this inner product.
I is the Malta index?
Yeah. So this is the kind of round on this. So I1, I2, I3, and J1, J2, J3. No. This is just 0 to n, so far. It's just a simple index. In some cases, it becomes multi, but so far it's just a number from 0 to n. It's rank of H.
Sorry, is it G I1?
I1, 0.
0.
So 0 is a unit.
0 is unit, I'm sorry.
Yeah. And you can see that this is somehow very much similar to some kind of perturbative Chern-Simon type thing, but it's slightly different. But you can draw this as a Feynman diagram like this. You just wrote one circle and two vertices, and you put unit here, no, one here, and one here, and you put M here. And no, product. Product is M, M2. And so for this prevalent vertices, you put the product structure here. And for this line, two lines, you put this inner product. It's slightly different from usual Chern-Simons, because for Chern-Simons, for this line, you put propagator, but here we just take inner product.
This is exactly what conservative Chern-Simon model was associated with, right?
Really?
Mm-hmm.
It's written somewhere?
Yeah, they have this at the end of the infinity algebra paper.
Oh, really? That I didn't know. Okay, yeah.
And this is exactly
Do they think of it as like a class in the cohomology of the moduli space, or no? What is the number?
No. This is the evaluation of the corresponding class in the moduli space on the infinity algebra, on the Frobenius algebra.
Oh, yeah. Maybe there is some. Yeah. Okay. But anyway, so
What I mean is, this is what they would associate with this particular graph.
Yeah. That's true. Yeah. And so what one can first say is that this number is independent of the choice of basis. That's a kind of very simple tensor calculus. I mean, you need something like a sign, so it's kind of super tensor calculus, because you have one lower indices and one upper indices, so you can just take sum by Einstein rule. So you can just take very simple algebra. If you change the basis, you get the same answer. And so this means that if you have any Frobenius algebra, you get number. Unitar Frobenius algebra, you get a number. And so this is a kind of purely algebra, simple algebra definitions. And I want to write down some theorems. So because this is purely algebra, so I want to write theorems. And this is in a book. Plus, so this is a kind of I think MSIP 46. I don't remember. And this is in a kind of archive. So this is something called cyclic symmetry papers. And what I wrote, except cyclic symmetry, is in this book, and cyclic symmetry is added on this paper. The statement is the following. If L is X, and X is symplectic, and L is Lagrangian, and relatively spinning, and then this cohomology, maybe it's like lambda, is a cyclic filtered infinite algebra. And I don't want to define cyclic filtered algebra yet, but it gives this Frobenius algebra in some context. That's something I want to explain. So this theorem is in these two papers. And this, except this cyclic, it is proved here, and you can just add cyclic symmetry like this. And so this cyclic symmetry gives some element mk. Let me write it h from h of x tensor k to h of x, and of course the unit is just I'm sorry, unit tau. Unit is just a fundamental class, and Poincare duality, this inner product is a Poincare duality, up to sign. And then I want to associate. So then you do some algebra. We can just associate weak bounding chain. It's just a set of B on this odd cohomology. Some coefficient. I just want to, so that if you take this sum over all this sum from 0 to infinity is something like a constant times this unit. So unit is a kind of Poincare dual of the fundamental chain. So this is called a weak bounding chains. And then yeah. Sorry. And then what we can do is the following things. No. This is completely general. Yeah. And everything is just in this case disintegrated. So, and then if B is contained in this M weak tilde of L, then you can cook up this H. No. You have a kind of M1 B. It's a map from homology to itself, and Floer homology of LB is just a kernel, and under these conditions, so this is just a boundary operator, and then this one is a kernel of M1B divided by image of M1B, and then we can so then there is a M1B is something like a deformed of this MK by B, but I don't want to explain this in detail because this is. So then because this is H, and the H and the Poincare pairing and M2B up to sign, and the unit is Frobenius algebra. So that's a kind of purely algebraic story. You have a cyclic infinite algebra, you can just take a homology, you get Frobenius algebra. And then this Z gives an invariant. So we have a map Z1, which goes from this weak bounding chains to lambda, which associates to B to this Z of this unit. So this is a kind of numerical invariant. And I just remove tilde because somehow there are some gauge equivalence, and what we get is invariant of the gauge equivalent. So this is a kind of first, and probably this is a kind of one loop invariant for this. And there is something called G0, and G0, and actually this we wrote it potential functions, or maybe this is superpotential. And this is something, so you put B, then as I wrote here, this Molar-Cartan type things is some constant times this 1, and this C is by definition is the 0 of B. So this is a kind of value of Landau-Ginzburg potential in some case. So you're just kind of superpotentials. This is G0, and this is G1. And maybe if you just honestly write G0 using a similar diagram, then G0 is something like this. You have a unit here, and you take this M0. So this is kind of Z0, and Z1 is something like this. There are two invariants, and now what I can say is the following things. So this is a kind of invariant, and in some cases this one is kind of very small, like a finite set or 1 point, and then you get a numerical invariant where Lagrange sum manifold. And the remark is the following. Suppose that in a Calabi-Yau situation, Calabi-Yau means that C1 of x is 0, and you assume that eta of L, H1 L to 2 of Z is 0, and so this is the Maslov index, and you assume that mu of L is 0, and you do not know the Maslov index. Maybe you can just imagine that L is a special Lagrangians of your Calabi-Yau manifold. Then this Z1 is actually 0 whenever it's defined. And I don't want to explain how to prove it, but it's very easy because these two conditions mean that somehow you have a Z-graded, not a Z2 graded. And in the Z-graded case, if you see the degree issue, so I draw some formulas, and this kind of each factor has some degree, and then the degree does not match. So if you just count the degree, then degree is not correct. So you don't have any non-zero terms. So it's just 0 in the Calabi-Yau case.
Is it important that this is odd-dimensional, Calabi-Yau odd-dimensional?
No, it's true in any dimension. It's different. I mean, in a case of this perturbative Chern-Simons type things, you need 3 dimensions.
I'm just used to the B model case. What this would give is the alternating sum of the dimensions of the X groups of a brane with itself. That will be 0 in the odd dimensional.
No, this is just a dimensional counting. So it's a kind of dimension is somehow much smaller than an M. I mean, you need some kind of a moduli space of rather big dimensions to get this sum to be non-trivial. In the Calabi-Yau case, the dimension is smaller. It's not a parity. It's just a kind of, it's not enough dimension. I think for the story of perturbative Chern-Simons, it's kind of a different story. And what this something involving a unit is a strictly different story. That's somehow I want to make very clear.
For quantum cohomology, what is Z1?
No, the quantum cohomology, I never thought about it, but it's kind of probably 0. Because in the same simple case, like it's a direct product of trivial things, right? So, I mean, so let me show you some example of this calculation of Z1. Then you see what it is. But what I want to emphasize here is that in a case of this special Lagrangian Calabi-Yau, that's the most popular case in Miller symmetry. Then this Z1 is just 0. So this is the kind of so then Z1 can be non-zero. Mainly in Fano case or toric case. So this is a kind of invariant of this. So there is an invariant which came in a Calabi-Yau case that I say I don't talk, but it's related to this something like a quantum version of perturbative Chern-Simons invariant. That is non-zero Calabi-Yau and 3 dimensions. That's one case. But the case I'm interested in is a case of this Fano or toric. And in that case, you have a big Maslov index. Then you get this non-trivial invariant. So just something I want to explain. So I want to explain some example. Then you see what kind of invariant it is.
Is the one the same as the Euler characteristic
Of
this H?
No. It's completely different. So example is the following things. So let me take this H. This guy is so-called the cyclic Clifford algebra. Is the following things. So in this case, let me take rank of H is 2 to the power small m. And then we assume that you have a E1, En to H. It's not a basis. This is much bigger, but you can imagine that H is a kind of cohomology of the tori. And then this E1 in here is something like a generator of fast cohomology. And then Clifford, so let me assume that it satisfies Clifford relation. So I want to define this cyclic Clifford algebra. The definition is that, so the defining relation is EI EJ plus EJ EI is 0 or DI. This is the case I is not equal to J, and if I is J, it is this DI. And DI is some number in lambda, and usually I want to assume it is non-zero. So this is the famous Clifford relations. And then of course, using it is very famous that E1, En generates some H, because the Clifford algebra, so this is the only relation between EI and J. So you have a Clifford algebra generated by this one. It is exactly this rank. So you get a Clifford algebra. So this is, of course, Clifford algebra. And so in this case, I is something like I1, Ik, it's a kind of 2 to the power n. So this is a kind of subset. So now large I is a multi-index. And this is large n. Then, of course, this basis, EI, is EI1. So this is associative, so you can just write it like this. EIK. And then E empty set is just a unit. So maybe write it to 0. So EI is a basis of H. So this is so far only for the Clifford algebra. This is very well known. And the cyclic means the following. So I want to define inner product by the following relations. It is plus minus 1 or 0. And this one is equal to that if I and J are disjoint, and if the union is everything. And otherwise it is 0. And this sign is just a kind of a signature from 1 to n to this I and J. So you have some sign. So you get, so this is the definition of the cyclic Clifford algebra. And in this case, this invariant is non-trivial. And the calculation is very easy, and I don't want to explain, but you can just calculate by this using base, using definitions. It is just d1 to dn. So you take this di, you can just take its kind of determinant of this quadratic form associated to this. So this is a typical case that this invariant is non-trivial. Okay. So I want to explain how this kind of this cyclic Clifford algebra appeared in a Lagrange Floer theory. And of course I want to, so then I want to talk this Lagrangian tori in X. And I want to assume one condition. Star is the following things. So suppose beta is relative pi 2, and assume, I assume explain what it is. This is modular space is non-empty. Then Maslov index of beta is non-negative, and moreover, if it is 0, then the beta is 0. So this is assumption. This is assumption. This is not a statement, this is assumption. And M of beta is just a compactification. Of the modular space of holomorphic disk. Is holomorphic with homology class is better, and we divide it by this PSL to R. It's automorphism of disks. So I mean, suppose you have a holomorphic disk of homology class beta, then Maslov index is 0 or higher, and if it's 0, it's trivial. So this is kind of very much a Fano type conditions. I mean, in an absolute case of this quantum cohomology, then this is something like a Fano condition. Then you have a relative version of Fano conditions.
This sort of property wouldn't be invariant under changing J.
No, that's right. And this is kind of a simplifying assumption. We can prove this. And then the statement is the following. The theorem, I don't know if we wrote it in a book, but in our paper, but maybe we basically prove it. It's a kind of following things. So suppose that this assumption is satisfied. And then, first of all, this I wrote this weak modular space of weak bounding chain. This contains first cohomology of L, lambda 0. And I say that this weak bounding chain is a kind of solution of the Molar-Cartan equations, constant times unit. So this is the defining equation of this weak bounding cochains. And a priori, there is no reason at all that this is has a solutions. But in this kind of Fano situations, we have always solutions because H1 is always satisfies this assumption. This is the first part. And then the second part, then if B is contained on this weak bounding cochains, and so then we can cook up this M1B, and we assume that this is 0. Then, of course, in this case, so this means that the Floer homology is usual homology. Then we have H. It is a homology of L. Together with this M2B and Poincare duality and unit is a cyclic Clifford algebra. So this cyclic Clifford algebra I just explained appeared under this Fano type assumptions. I think except this cyclic statement, then Cho proved very similar statement. I mean, in a toric case, Cho proved many of the Lagrangian fibers is a Clifford algebra. And we can just get a bit more arguments to prove that this inner product is actually the correct form, as I explained. But for this, we need two things. We need this this kind of assumptions, and also we need cyclicity.
Why do we get non-degeneracy? Why do we get non-degeneracy after?
Oh, I see. I'm sorry. Yeah. So di is 0 is not proved. Oh, I'm sorry. So there are some di, so that is cyclic. Yeah, you're right. Yeah. So this is a general statement, and I can say a few more words. So this means that for this kind of situations, this invariant is this product of di. So it's kind of natural assumptions. And let me explain that this star is satisfied. Star is satisfied either in the following two cases. The first case is I think so Mx is toric, and Fano, Nef. I'm sorry, Nef. It's a bit more general than toric. Nef, and L is fiber, an orbit, Tn orbit. So in the case of toric fibers, then most of this kind of assumption is satisfied, but you need the Nef assumptions. Because somehow we put this compactification. So in the case of this negative sphere exists, then the bubble does not have correct Maslov index. And the second case is rather easy. You just assume that the complex dimension of X is 2, and J, almost complex structure, is generic. And then we can just prove this by dimension counting. So you have two cases. So in these two cases, then the Lagrangian tori, if this M1 is 0, is a cyclic Clifford algebra. And of course, even in the case some di is 0, then this equality that z is equal to the product of di is correct. But in that case, the invariant is just 0. So it's kind of sum of the zi. And in some note is just kind of suppose that X is toric without any this Nef conditions, and L is Tn orbit. Then we can still prove under this assumption. So then we can prove the first one is correct, but the second one we can prove that this Floer homology, homology of L, is isomorphic to the Clifford algebra as algebra only. This means that here I say that it's a cyclic Clifford algebra. This means that not only its algebra structure is a Clifford algebra, but its inner product is in a standard form. And actually, I made some misunderstandings. So for a while that I thought that we can prove that this cyclic Clifford algebra property in general for any toric manifold. But then there is some problem about the compatibility of cyclic symmetry and the perturbation of the moduli space. And that prevents us to prove this in complete generality. And so far, we can prove only in the case of NEF. And I'm beginning to suspect that in the general case, it is Clifford, but not cyclic. So this means that it has some different effect for this inner product. And I'm beginning to suspect that this extra effect is related to the primitive form. So maybe I'm going too much. Maybe I don't want to talk. So now this is a statement, and then I want to show you how in this case what happens. So let me write this W. So I want to assume this. So I want to consider this case, and the W in this case is a function. So this is what I wrote Z0. Lambda 0. Yeah, this is safer to lambda, and this is contained in this weak bounding cochains. And then this W is a functions. And so this is a kind of Landau-Ginzburg potential. Potential in this case, in this phenotype case. And then I want to rewrite these second conditions in the following way. And then the first, it's also in a similar way in this paper. So B, so let's take B in H1. I'm sorry, it is safer to this, but this is H1. No, this is okay. This is okay. Yeah. Yeah, it's safer to write this is H1. Otherwise, the degree does not work. So suppose that H is H1, which is contained in this. Then M1B is 0, if and only if this W is critical point at B. So you say that your W is a function of first cohomology. It's a Landau-Ginzburg superpotentials. And the conditions that this the boundary operator of the Floer homology is trivial is equivalent to the condition that this B is critical. So that's the kind of general calculations. And then in this setting, then in this DI, I is 1 to n, IM value of this Hessian matrix at B. And here, let me write this. So H1 of L, this is a kind of Z to the power n, right? This is a tori. And E1, blah, 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 En is a basis, natural basis. And B, I will write this Xi, EI. So EI is just a coordinate here. And you use this coordinate, and the W is a function of this Xi, is a natural coordinate of this first cohomology of the tori. And you take the Hessians, and this Di I draw is a eigenvalue. So this means that the Z1 of this L of B is just a determinant of the Hessian matrix of this W at B. So this is a kind of a familiar invariant which appears in this Landau-Ginzburg potential strings. But so what explains that kind of this kind of invariant is exists in general, and in this particular case, it gives a Hessian determinant. Now, I want to explain a bit more about this toric case, and I want to say some properties and some proposal how to generalize this kind of constructions. So the property is, So to explain these properties, I want to say something about cyclic cohomology. So as I say that this, if you have errors here, then this cohomology of L, is a cyclic infinity algebra. But this cyclic infinity algebra property is not so much necessary. So we just start from C and M. It's a kind of infinity algebra. Then I think what Mohammed used in the last talk is cyclic bar complex. Okay. C. It's right. So its element is so this is some BK cyclic. C is a tensor product of K copy of C divided by some relations, and this relation is just a cyclic equivalent. So you have a x1, xk is equal to their sign, xk, x1, xk minus 1. And using this mk operations, infinity operations, we can define, so this is a B cyc C. We can define cyclic the differentials. It's kind of okay. Then this is some kind of two type of the sum. It's a first sum is you can just take any of them. Then you can just take M inside xk, but as usual, as in a Hochschild M something complex, you have another term, zero sign. It's a kind of M and xj, blah blah blah, x. I'm sorry, this is k, right? Xk and x1, blah blah blah, xi, and xi plus 1, blah blah blah, xk minus 1. So this is the usual cyclic differentials. I mean, usually cyclic homologies for the DGA or associative algebras, but this generalization is quite straightforward. I don't know if maybe it is written in some paper like Getzler-Jones or something like that. Yeah. And this cyclic homology is this homology. So this homology of this is a cyclic homology of C. So now, as Mohammed mentioned, that in our book we define some, in this setting we define some operator B, which goes from this cyclic homology of this Lagrangians to the ambient homology. This is just using this output, and you have a P input. This is beta P, and the claim is the following. So the meaning of this invariant Z is the following. So we consider an L, B. So L satisfies the star, and B is an element on H1 of L, so that M1B is trivial. Then I take this P of this 1 tensor exponential of B, and P of this 1 is unit of exponential B. And so this is an element of ambient homology. So we take this ambient Poincare duality X, and the claim is that this is Z1 of the Floer homology of L at B with respect to this M to B and the Poincare duality and 1. And actually, we wrote this so far. The proof, I think, better to say that maybe like a claim, but this is a theorem maybe in the case when there is a toric and a Neff toric, and this is let me see. We don't use Neff assumption in this case, but it's a more subtle, so let me write it to Neff. Neff toric in the case when Neff toric and it's a fiber. Without the proof at least. And I think that this falls in complete generality under this assumption stuff. The proof goes through. And the proof of this theorem is similar to this annulus argument or Cardi relations which appeared in the last talk, but I don't want to explain it. But so this is something like an argument for this, how this Z1 means. It's a kind of reflection of the Poincare duality on ambient space. And then I want to mention some corollary of the example in the following. So suppose that X is toric, X is Neff toric for simplicity, and then using this actually Z1, we can just generalize it to complete toric case, but I want to make it precise to the Neff case. And then you have some finitely many Li, Bi. Let me, again, for the simplicity, you assume that quantum cohomology is the same simple. And then you have some kind of 1 to B. B is a rank of the cohomology. So you take this Bethe number and you have finitely many collections and Lagrangian plus Bi, so that M1 Bi is 0. This means that the Floer homology of this guy is just the homology of the tori. I see this. Sorry, this Li is a Tn orbit, and Bi is a element of first cohomology. So you have exactly the choice equals the Bethe number, so that Floer homology is isomorphic to classical things. So you can define this invariant Z1 for this, but then, for example, that's a claim that corollary, maybe of this kind of claim, and also something else is that you take the sum over this Z of this Li, Bi over 1, and this is 0. So this is some kind of a residue formula. And also for this, in this case, of course it is same simple. So quantum cohomology of X is just a product of the direct product of this B copy. Maybe I will take Novikov ring over complex numbers. Then the ring is algebraically closed. Lambda is algebraically closed field, and some simple algebra over algebraically closed field is just a product of finitely many copies of the ground field itself. And the rank is, of course, the Bethe number. So you have this B copies. And then we can say that if you take this P of this 1 of E of B, this Li Bi, one of them, is equal, divided by this Z1 of Li Bi is a unit of ice factor. So let me say that the P gives a map from the element of Floer of the cyclic cohomology to the quantum cohomology, and the quantum cohomology is split into B pieces, and each piece has, of course, a unit. And those units came from this ice component of the ice non-zero Floer homology of this Li. But you need to change this guy. And you see that this fact and these formulas plus simple fact that if you take a unit of this X and unit of X and the Poincare duality of X is 0, right? This is 0-dimensional class, this is 0-dimensional class, a cup and it is 0. Then you sum up, you get this corollary. So, but of course, maybe this kind of thing is more important than the corollary itself. So, but let me check this corollary in some particular case, because somehow after we found this kind of things and when I saw this corollary, then this is rather exact equality. So I was rather afraid that we made some mistakes, and we checked some. I calculated some examples. It takes some fortnight, and it is finally correct. So that makes me happy. So I want to mention what happens in that case. So that's the case when x, example, let x is a monotone blow up, monotone 1 point blow up of P1, P2, I'm sorry, P2. So then of course there's a batch number is 4. And you take L, X is a kind of, there is unique monotone, Tn orbit. And then the W for this L is something like this. T 1/3 y1 plus y2. So this kind of calculation you can find in a toric paper. Plus y1 inverse. So this is an easy calculation. And this yi is e to the power xi, and xi ei is an element of h1l. This is lambda 0 square. Right? This is a torus. So you take the exponential of the coordinate, natural coordinate of the first cohomology, then you can calculate this lambda Gizmo superpotential explicitly. It is this function. And there's a monotone 1 point blow up. Then there's this formula. Then we take this conditions that this superpotential is critical. That's the condition that this. So let me remind you that this is equal to this M1B is 0. And this condition you can just by this elementary calculus you can just differentiate. So it's a kind of, you can just calculate. The solution is y1, y2 square is 1. This is, you can check easily by this -1 is 0. Right? And then Z1 is of course a Hessian. So in this case Z1 is Z1 is a determinant of this W, but you need to take this xi as a coordinate, not yi, but xi. And this you can calculate explicitly in this case. It is, I think, t 3/3 4 minus y2 cube. I think I use this relation for this calculation. So this is y2. And then this formula is equivalent to this y 4 minus y cube, and y solves, and the sum is that y solves this equation. So you have this equation of degree 4. You have 4 roots, and you plug in the 4 roots here, and you sum up this, then this should be 0. And that I checked. It takes some time to have some elementary algebra, but it's correct. So you see some feeling how this invariant is. It's a kind of invariant like this, and you have similar equality for any Fano or Neff-Calabian manifold. And of course, this is a point where everything is monotone. Then you don't have any t here. But if you go to generic point, so this is not a kind of more complicated equation. You have an infinite series of t, but you have still the same equality. But I think we can check this directly as a kind of good test that are certainly correct, because it goes somehow a long way to prove this. So I'm not afraid, but it's okay. So now in the rest of my talk, I want to explain some potential generalizations or some relation to some other stories. So let me remind you that in this case, we start somehow Z0. Here you have M0 and 1. And Z1 is something like this. 1, 1. So you can expect very naturally, so what is decay? Right? You may continue this kind of stories to get and you have some kind of story which is very similar. It's a kind of story of perturbative Chern-Simons. It's Calabian case. And in Calabian case, you have many different kind of diagrams consist of this kind of disks, graphs. and you put the propagator here, and then you put the infinite operation here, but no unit. Then this looks very much similar, so I expect that there is a similar story. So I just want to say a few words how it should be related. So I want to mention some theorems. This is very classical, and I think I asked this kind of things to Muhammad, and he told me this reference. It's the following things. So suppose that HM is an infinite algebra, and we assume that M0 and M1 is 0, and we just so in this case you just take H and M2. I'm sorry, maybe unit. And unit, this is a kind of associative. This is the associative algebra, and we assume that this is isomorphic to Clifford algebra. And then we consider cyclic homology of this H, and I'll explain what this filtration is. And this is 0 or rounding. This is k odd, and this is k even. And let me say that this fk of b psych c is just a sum over L is not bigger than this b psych LC. And using these assumptions, especially this M0 is 0, this one respects the cyclic boundary operator. So this one respects cyclic boundary operator. So this gives a filtration Fk cyclic homology of H. Right? And this is a subcomplex, so you can just take an image of its cohomology, cyclic homology. And this is this Fk. I mean, in the case of this associative algebra, not cyclic algebras, and then this complex is actually graded. This cyclic boundary operator is kind of, if you take this number filtration, then it's degree -1. So it's a graded algebra. But in our infinity case, it's not graded. It's filtered. And then you can say about and this Cassel, this cyclic algebra itself, Clifford algebra itself, and in that case, this graded algebra, it is 0 in odd dimensions. It's a ground field in even dimensions. It's what he proved. But then we can just simply generalize it, and yeah. And then what we can say is the following things. So next thing is the following things. This is kind of also well-known things. I don't know who first proved it, but you have the kind of Hochschild cohomology of this H. This is controlled. Control the deformation of cyclic infinity algebra. This means the following thing. So you have this fixed H and MKT, and you have so I just move these operations, and then if you take this derivative, so this is the kind of cyclic infinite algebra. I'm sorry, I don't define cyclic infinite algebra, but it's a kind of infinite relation plus some cyclic symmetry of the operations. And then I take this derivative of this operation at t equals 0. Let me write it AK. And then this together, 0, 1, blah, 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 is an element of the cyclic chain of this H. And this is a kind of boundary H is 0. So this gives an element of the cyclic homology of H at MK0. So this just means that the tangential complex of this deformation of cyclic infinite algebra is exactly the cyclic homology. So it's very naive things. So now what I want to say is the following things. So we consider this family of cyclic infinite algebra. So I will take this Z1 of H MTK inner product 1, and then I take this derivative, and this t equals 0. And then this gives some map. Let me write the Z1 of the cyclic cohomology of this H M0 to the ground ring. And the claim is, so this is rather easy, so I will try the propositions. It's just if this, if H, so if this M0, M star. M0, M1 at Z is 0, and M2 is Clifford. And then maybe DI is non-zero, probably it's better. Then this one induces isomorphism for this F2, F0, and lambda. As I said, that this theorem, the Cassel says that this second filtration divided by the first filtration is this lambda. And this isomorphism is actually realized by just differentiating our invariant. And this F2 just means that F0, F2 means that you have only an algebra, M0, M1, and M2. So as far as you consider the deformation of this Frobenius algebra, not the cyclic infinity algebra, then this is a kind of perfect invariant. So this Z1 somehow completely controls the deformations at the point of this Clifford algebra. And then a problem. So I want to propose the following problem. Find Zk of this invariant is a kind of invariant of homotopy type. There is a notion of homotopy type of cyclic infinity algebra, such that you can just take this Zk in a similar way. That's just this gives a control of this F2k, 2k inverse goes to lambda for Clifford algebra. So I believe that it's kind of rather combinatorial algebraic problem. So you have many operations, and you want to cook up the numbers. And the number, to cook up the number should be something like, so the Zk should be written some kind of, Zk should be some kind of sum over the Feynman diagram. Something like this, right? I don't know. Right? The simplest one loop diagram we get Z1. And then probably it's very likely that you can just generalize it to get the same number. But I don't know how to do it. Probably it should be possible in the near future. And then I want to say a few more words. What time? Yeah. So a few more words how this should be related. So there is some conjecture by Giventhal and something related to this. So let me consider this W. It goes from H1 of L to lambda. And then I want to consider this oscillatory integral W y1 yn divided by H and D y1, y1, e, yn. Honestly, maybe we need to replace this by some other primitive form. So, at least in a Neff case, I believe that this is the correct primitive form. But in a case where it is not Neff, I don't believe that this is not a correct primitive form. But anyway, let me consider this oscillatory integrals. And then I want to consider this asymptotic expansions of this. And this is a kind of classical story that the asymptotic expansions of this is a kind of a critical point of W that's related to this pair, this B, for which M1B is 0, right? It's a critical point. And then if you see this first one, it's a kind of value of E equal to -1. Let me write it this Z0, right? H and the Hessian here appears as a Z1, right? So you have the square root of determinant Z1 of LP. And then you have a 1 plus some L of the some CL of H of L, right? And the conjecture should be that the CL should be some this dk. Probably 2L or something like that. So this asymptotic expansion should be this this kind of a Feynman diagram, and this should be this invariant which detects this higher cyclic homology. And what I think Giventer wrote somewhere in his papers is the following conjecture, right? I mean, Giventer said that this CL is something related to this higher sum of the CL. Some of the higher genus Gromov-Witten type. Maybe I just simply write the Gromov-Witten invariant of ambient space, right? Of X. And asymptotic expansion of the ambient space, asymptotic expansion of these potentials, and this higher thing knows this genus 1 or genus 2 higher things. And so this is just a problem. So I just want to pursue this line, but still it's very difficult to do. But first I want to understand is that I want to find some kind of a expression of this by using Feynman diagram of this higher invariant, which detects this higher cohomology, higher element of cyclic cohomology. And this diagram, this sum should be control this higher order term of the asymptotic expansion of this usual oscillator integral of superpotentials, and then we get some information. I mean, but there are some other things, so I don't know how much I can do. Okay, thank you very much. I stop here.